For all of human history, we have looked up at the night sky and accepted the moons circling above us as finished objects. They feel permanent, fixed, and incredibly old, like a background element of the universe that has simply always been there. Take the massive icy satellites orbiting Jupiter, like Ganymede and Callisto. These are giant frozen worlds that swept up their material and locked their complex surfaces into place more than 4 billion years ago. Every rocky crater and frozen plain we can study in our neighborhood is a completed artifact. We have never actually watched the recipe of a moon being followed from the beginning. Because we arrived billions of years late to the process, the actual physical steps of how a moon is built have always been hidden from us. But 625 light-years away, there is a star cataloged as CT-CHA-A. It is barely 2 million years old. Against a universe that has been expanding for roughly 14 billion years, 2 million years is younger than a newborn. The dust here has not even settled yet. Looking at a system this young gives us a rare window into an active construction yard. We get to see the raw ingredients being stirred together before a single finished moon actually exists. The focus of this system is a massive gas giant called CT-CHA-B. It is so young that it is still settling into itself, glowing brightly with the heat of its own recent creation, and it sits in almost total isolation. The gap between this infant star and the growing gas giant is enormous, roughly 46 billion miles of deep cold. Pluto sits roughly 3.5 billion miles from our sun. This new planet orbits 10 times farther out. Out here, the planet pulls in surrounding material, forming a spinning ring, a circumplanetary disk. Inside, microscopic dust grains collide, eventually accumulating into massive solid bodies. Sitting far away from the chaotic heat of its parent star, a massive planet acts as its own gravitational anchor, quietly building a miniature solar system from the material trapped in its orbit. Identifying exactly what that material is made of is incredibly difficult. Trying to read the faint glow of a thin ring of dust while the planet's host star blazes right next to it is like trying to read a label on a candle held in front of a stadium floodlight. To cut through that glare, astronomers turn to the James Webb Space Telescope. Its mid-infrared instrument is specifically tuned to detect the faint thermal signatures of molecules freezing in the cold depths of space. Webb managed to separate the light of the young planet from the star. It then spread out that tiny sliver of light to read the specific infrared wavelengths emitted by individual gases, effectively scanning the chemical barcodes of the dust ring. The results revealed a chemical kitchen heavily stocked with carbon. The telescope detected 7 different carbon-bearing molecules floating, including acetylene and complex rings like benzene. But when astronomers pointed Webb back at the broad sheet of material orbiting the central star, they found 0 traces of those 7 carbon molecules. Instead, the primary stellar disk was dominated entirely by oxygen-rich compounds. These 2 rings formed from the exact same initial cloud of interstellar gas, yet in only 2 million years, the primary disk around the star and the secondary disk around the planet have drifted into completely opposite chemical realities. The chemistry inside these rings dictates exactly what the resulting moons will be made of. The molecules swirling there are the building blocks that will eventually bake into solid ground. In our own solar system, the raw materials leaned heavily toward oxygen. That chemical balance gave us silicate rocks, ocean-covered worlds like Earth, and the thick shells of water ice wrapped around Jupiter's moons. This diagram illustrates what happens when you flip that ratio and let carbon dominate the mix. A moon forming around CT-CHA-B would likely skip the familiar water and silicate rock, condensing instead into dark, sooty, carbon-heavy materials. This single, distant disk proves that the early conditions for planet building can differ wildly even within the same star system, carving out paths to entirely alien worlds that our local neighborhood never experienced. What makes this observation so rare is that the disk is pulling double duty. The material feeding the seeds of these potential new moons is simultaneously raining down to feed the giant planet, which is still actively growing beneath them. When we look back at the pale, finished horizon of our own moon, it is easy to assume it was always meant to be there. But worlds are built. Slowly, Chemically, grain by grain, out of dust and gas clouds, the universe is entirely capable of assembling things we have never stood upon, and out in the dark, the workshop is still open. If you want to explore how the universe puts itself together, consider subscribing to the channel. There is a whole library of journeys waiting for you, from the mechanics of black holes to the strangest planets we've ever found. Leave a comment with a piece of the sky you'd like explained next, and until then, keep wondering what else is out there waiting to be seen.